Hello everyone, welcome to this video. Today we are going to look at this integral. Now, this is a very advanced integral that I'm going to solve for the first time on this channel, and I really hope it gets as much attention as it deserves. So this is a variant of a problem that got asked in a Cambridge entrance examination, specifically of the type 1B. But what we are going to do is we are going to find a general way to ensure that we find all such values of integrals of this pattern. Okay. So there are a few things you must know in order to do this integral because this is not going to be a basic integral, although not so much advanced. Like let's rate this integral out of 10. If I were to do that, I would do a 5 by 10 maybe, but still we're pretty much advanced than basic. Okay. First of all, I do not see a straightforward way basically to solve this integral directly. And people might try to do substitutions like log x and stuff like that. And I do not know that will like whether that will work or not. But my initial intentions, whenever I see a log x to the power something, and then a polynomial equation in the denominator, and then you have like 0 to infinity and stuff like that, I immediately recall the identity d dx of a to the power x equals to a to the power x log base EA, of course. And this is the identity that we're going to base the whole problem of. Now, let me show you how. So first define a function with respect to a parameter s as follows: 0 to infinity, x to the power s divided by 1 plus x dx. Now, there's a specific reason of doing so. Let's make this x square actually. There's a specific reason of doing so. First of all, you have to notice that this is a convergent function. So this function converges, but only for values where 0 less than s less than 1. And also, this function, if you were to differentiate this function like 4 times, so basically this thing would give you 0 to infinity x to the power s. And as I told you earlier, we are going to differentiate with respect to s and not x because we cannot even differentiate with respect to x because it's a dummy variable, right? It's inside the integration. It's not really a variable. It's just acting as one. But s is a real variable here, which with which respect to which the function is defined and the answer is got. So we can differentiate with respect to s. And if we were to follow this particular formula right here, what we would get is every time we differentiate x to the power s, we'll simply get x to the power s times a constant, which is a constant with respect to s, which is log x. And by doing it 4 times, we will get 4 times that constant, which is log x to the power 4 divided by 1 plus x squared dx. Make sure you do not have any doubts here. Okay. Like when you're differentiating with respect to s, you can imagine this situation where x is the variable, where s is the variable, and x here is the constant, which here in case is a. And that is why every time you get the same thing multiplied by log x. So in this case, log x. And now if you put 0 in this function, you get your desired integral, which we are trying to find out, which is log x whole to the power 4 by 1 plus x squared dx. So our goal should be to find the function f and then differentiate it 4 times and then put the value 0 and finally get the answer, correct? Okay. Now, how do we do that? Let's see. So first of all, f of s is simply 0 to infinity x to the power s divided by 1 plus x squared dx. Make the substitution t is equals to x squared. This would give you, I think, dx equals to dt by 2 root t because x is root over t, and then you differentiate both sides. You get dx equals to dt into differentiation of root t with respect to t, which is 1 by 2 root t. Put this value in. The limits will remain unchanged because for value x equals to 0, t also goes to 0. For value x equals to infinity, t also goes to infinity. And x to the power s basically becomes x to the power t by 2. 1 plus this one becomes, I think, 1 plus t. Uh, by the way, okay, x to the power s actually becomes x to the power s by 2, not t by 2. Okay, so this ensures that we have dx left only, which is dt upon 2 root t. And okay, wait. You need to make this one t to the power s by 2. That's what I was confusing here. So this is t to the power s by 2. And finally, the integral basically becomes 0 to infinity. Let's put the half outside, t to the power, and this becomes t to the power minus half, s minus 1 by 2 divided by 1 plus t dt. And now I'm going to introduce another function, which is like uh, a variant of the beta function. So in general, if you know the beta function, or if you don't, I can make a video on it, or there are multiple videos already available. It's like this. So the beta function in general is defined as beta of AB, where there are two parameters A and B, and the integral is 0 to 1 x to the power a minus 1 divided by 1 minus x whole to the power b minus 1 dx. And this integral simply equals gamma a into gamma b divided by gamma of a plus b, right? Where gamma a basically is the gamma function. It's also defined the gamma function here. Gamma of n is simply 0 to infinity e to the power minus x to the power n minus 1 dx. For natural numbers n, this becomes n minus 1 factorial for n belongs to natural numbers. And for other numbers, there are different values because it's simply an integral. And this is defined for obviously n greater than 0. For those values, this is defined. Okay. So anyway, what I was trying to achieve here is beta of AB also has a different form. And the different form is given by this. Beta of A comma B also has a form with 0 to infinity, which can be achieved by certain substitutions here, which is like x to the power a minus 1 divided by 1 plus x whole to the power a plus b dx. This also gives you beta of ab. Now, Euler's reflection formula is a formula which relates a certain value of beta ab to pi and sine. So, Euler's reflection formula. Now, what is this? This states that for 0 less than s less than 1, I'll just state the real version of it. 0 less than s less than 1, gamma of s into gamma of 1 minus s is simply equals to pi upon sine of pi s. That is called the Euler's reflection formula. So gamma of s into gamma of 1 minus s equals to pi upon sine of pi s. And this exact thing right here is what we are going to need, because when you see this integral right here, what we have got, okay, so let's write f of s again. F of s basically, as we have got, was half 0 to infinity. The numerator, as you remember, was t to the power s minus 1 by 2, right? We can write it as t to the power s plus 1 by 2 minus 1 divided by 1 plus t dt. Now, if I were to tell you that this is just the beta function, you might disagree. But then again, if you remember, the form with the infinity form was x to the power a minus 1. We have our a. So, of course, there should also be a here. But it's basically power 1. Yes, exactly. But then the b is basically this. This is a and this is b, and they add up to 1. That is what the power of 1 plus t is. So basically, this is beta of s plus 1 by 2, comma. 1 minus s by 2 basically becomes, I think, 2 minus s minus 1, which is 1 minus s by. This is the value of f of s. We can transform it in terms of gamma function. This becomes gamma of 1 plus s by 2, comma 1 minus s by 2, actually two different gamma functions, divided by gamma of the sum of that, which we already know to be 1, right? And gamma of 1 for natural numbers, as you know, it is should be 0 factorial, which is 1. Okay. So the value we got is something like this, half, and then this formula, we can write this as s plus 1 by 2 into gamma of 1 minus of s plus 1 by 2. And since s is from 0 to 1, s plus 1 by 2 is also from 0 to 1, right? So we can safely say that this holds. And since this holds, Euler's reflection formula also holds. And then this value is nothing but pi by 2 cosec of pi whole into s plus 1 by 2. Okay. So that is the value of f of s. And now, when you got the value of f of s in terms of a simple trigonometric function, you can easily differentiate it four times. I have done it already and put zero in the value. Once you do that, the answer that you're going to get is something like this. So first of all, f4 of 0, what was our actual integral? F4 of 0 basically gives you our actual integral, right? And if you were to differentiate this function four times and put s equals to 0, you would basically get 5 pi to the power 5 by 32. And since this is equal to original integral, we can safely say 0 to infinity log x whole square, so whole to the power 4, right? The whole square would be even easier. And but would be done with the same method. Even you can achieve any basically any power of log x with this same method. Plus 1 by divided by 1 plus x squared dx equals to 5 pi to the power 5 by 32. And that is the answer. So you've learned a lot of new things here, like gamma, beta, Euler's reflection formula, differentiation under the integral sign, and how to tackle this kind of integrals. But these are the things you need to know in order to solve these integrals that come at such high places, like Cambridge entrance examination or maybe Oxford math examination. And as you go up the ladder in physics and stuff, the integrals and the difficulties keep on increasing. And obviously, infinite sums are also reduced, which are solved using integrals. Okay, so if you do like this video, please like and subscribe. And also let me know in the comment section how you like this video. Thank you.